In this video lecture, we're going to explore some perhaps unexpected application of Radon-Nikodym theorem, which is conditional expectation. We're not going to dig too deeply into this topic. It is a fundamental topic in the theory of probability, that of conditional expectations. So here's the definition. From its size, you can already see it's a rather convoluted definition, but it is a fundamental object in the theory of probability, martingales, and finance, and all measure theory-based probability, which is to use sigma algebra to represent information. Let's start simple. We have a probability space, and on that probability space we have an extended random variable x, and we have a smaller sigma algebra. And this is how this is when sigma algebras start to have a important role in the theory. They're not just this object that we had to accept because of the measure problem. Sigma algebras, they are actually useful objects. So what does it mean to consider a sigma algebra which is smaller or more coarse? So being a subset of F means G is coarser, in the sense that sets that can be measured, that are considered measurable with respect to F, may be not measurable with respect to G. And so we consider this a smaller sigma algebra, and we will define what is the conditional expectation of our random variable x given G. So it is, if we have access to all the information encoded by a sigma algebra G, can we, what is our best prediction for the value of x, okay, that we can make given that information? And the definition of this conditional expectation is the following. You're going to consider another random variable z, and we say z is the conditional expectation if it satisfies two conditions. First, z can be determined just by the information that we have from G, okay, and this translates as z being G measurable. Okay? Z being G measurable means we can tell whether z is less than or equal to whatever number just by this event is an event that is we can measure in G, okay, that we can determine whether it occurs or not just by having access to the events in this family G. This will be the first condition. The second condition is that when we consider the average of the variable z on any set A also measurable with respect to this coarser sigma algebra, it will coincide with the average of x. So z is the best possible representation of x, or the variable that best approximates x in a world where we have access to events measurable with respect to G. Here's a remark that you're probably used to already, which is when we say unique, it means in the almost sure sense. Okay, so what is the remark? It says if x has a conditional expectation, then it is unique. Okay, what does it mean to be unique? Well, what does it, for a random variable to satisfy this condition? Okay, so if z satisfies this condition and z is G measurable, then any other random variable satisfying these two conditions, this is condition number 1, this is condition number 2, any other random variable satisfying these two conditions will have to coincide with z. Okay, and this is what's being stated here. Well, it says if there is such a function, it is unique. Okay, meaning if we have another random variable w such that also w is measurable, also if W is G measurable and also W satisfies this, then W, these two conditions, then W has to be equal to Z almost everywhere, or almost surely, because this is a probability space. This is the uniqueness part. Okay? If there is another one, it is unique. And moreover, this is the best we can hope for, in the sense that if W is G measurable, if W is G measurable and W equals Z almost surely, then this implies that W also is a conditional expectation of X given G. So in this sense, it is unique, as we got used to this sense already because it showed up many times. So it's unique in the sense that if there is a different function, it coincides at almost every point. So if we think of functions being equivalent, if they are equal at almost every point, then the equivalence class is unique.